course. I call it the roller coaster unit, but really it's titled Work and Energy. And as you can tell by looking at the picture here, we've got a bit of a theme on the unit. But before we get to all that, a little bit is I call it Work and Energy, and what they do have a sort of intimate connection in that they're they're actually very similar. But energy is the ability to do work. And work is a transfer of energy from one type to another. So what does that mean? Well, if you have potential energy, that means, for example, you had a sandwich for lunch and that's given you the energy to, run cross country after school or something like that, right? And the running, the actual doing something is the work. Energy is this, it's in you that you can do something. And then work is actually the application of that, okay? And that's basically what I mean. And we deal very specifically with a definition of work that says that there's motion involved. So, work has a lot, we think of work in a lot of different ways, right? For me working right now, I'm working as I prepare this video, but I'm not actually going anywhere. So from a physics point of view, especially from a grade 11 physics point of view or grade 12 college prep physics point of view, I'm not doing any work because I'm not going anywhere. I'm not moving. Mechanical work is what we deal with, and it's the transfer of energy that causes motion. So we only define work as happening if someone is moving or something is moving. So some details about work that you need to know, and in the next video, not this one, but the next one you'll watch tomorrow, will be actually applying some formulas related to work, but this is the most common one. We give work the symbol W, and work has a unit of joules. And just to give an idea of what I mean by joules, joules are not something a unit we use very commonly. However, I bet you've all looked on your yogurt container or your granola bar and checked the number of calories. Well, a calorie and a joule are kind of the same thing. Similar, like, how a foot and a meter, they both measure distance, but a foot is the American, or what's it called, imperial way of saying it, and a meter is the Canadian, but also the SI, more international scientific community way of saying it. Well, joules and calories are exactly the same thing. So while it's difficult to sort of understand what a joule is, it is really, compare it to a calorie. If I could give you an example, we could just look up on the internet here. I could go, keep that open for later. If I could go convert, what was it, maybe say Big Mac, well, number of calories in a Big Mac, let's find out. I think it's about 600 or something. So if a Big Mac has, come on internet. Uh-oh. My presentation is falling apart. There we go. A Big Mac, let's just say 550 is correct. Okay, so 550 calories in a Big Mac. Now I'm going to say convert 550 calories. See, it says here's something I have to tell you. It's kilocalories. When we read the number of calories in a Big Mac or in a granola bar or whatever, it's actually called kilocalories. It's actually 550,000 calories. Now I'm going to convert that to joules. So it's 2 million joules. So if you look up your Big Mac and it says you're eating 550 calories, you're also eating 2,300,000 joules. It's the same thing, it's just a different way of saying it. Okay? We'll actually do that a few times. Anyways, here's the formula for it. Work equals force applied times cos of an angle. And this is only if the force is applied on an angle, and you'll see tomorrow what I mean by that. Times delta D is the distance displacement being traveled. We never deal with direction with work. It's always just, work just is. Calories are just calories. Joules are just joules. There's no direction associated with them. Okay, so just to see an example, we'll do a lot of these tomorrow's lesson, but let's just see what I mean by this formula. So Aragorn drags Gimli out of the lake. He applies a force of 250 newtons at an angle 45 degrees above the horizontal. So he's kind of pulling up on him. Okay, he drags him 25 meters. How much work does he do? And you go through the calculation, and he does 4,419 joules of work. Just to get an idea, so what is that in calories? So did he burn off a burger? Did he burn off a Big Mac and dragging Gimli? Let's see. So convert, I'm going to say convert what did he do? 44. Oops, remember. 4,419. I have to say joules to kilocalories. 1 kilocalorie. So he burned 1 calorie. So if he did that 550 times, he'd burn off a whole Big Mac. Okay? You know, in your body, by the way, even if you sit and do nothing all day, you burn 2,000 calories. So this is only the calories burned in the actual act of doing the job. And then you have to include the fact that, you know, his metabolism was working at the same time. His heart was pumping. This isn't, this 4,419 joules only includes the actual dragging process, you know, useful work done. It doesn't take into account all the other stuff going on in your body to make that happen. Okay. Okay, this is just a definition thing, but you can sometimes have a force applied and actually not accomplish any work. And my example here is Sam's pushing on a boulder, and he pushes with all his might. He applies 175 newtons, but he can't get the thing to move. That means that even though he might be building up a sweat doing this, he's working, he thinks he's working so hard, but from a physics point of view, he does no work. And like I say here, an exercise such as a plank is 0 work, according to the physics definition. Doesn't mean that if you're doing a plank, you're not doing any exercise or burning calories, because you know you are, because you start to breathe heavy. Get yourself in the position long enough, you start to breathe heavy, you start to sweat. I mean, there's stuff going on there. And that's because in the microscopic level, you definitely are, you know, on the cellular level, you're definitely doing work. But from a physical point of view, what we can recognize and see and measure, you're not doing work. Okay. Another example, and this is always think of as a silly one, but I have to tell you anyways. The idea of doing work on something. So if Frodo's walking with the ring and he's got it in the palm of his hand, and he's walking forward. So he's moving, he's applying a force on the ring to keep it from falling, right? But the thing is, because his motion and the force he's applying on the ring, he's applying a force up on the ring, right? Because they're at 90 degrees to each other, we theoretically call that no work. He's not actually doing any work on the ring. Anyway, that's a definition for work, 0 work. So there's 2. One is if force and no displacement, and the second is a displacement, but the force and the displacement are at 90-degree angles to each other. Okay, and then there's negative work. And this makes sense if the force is in the opposite direction of the motion. And what that really means is if the force is causing the motion to slow down. And of course, that's almost always going to be friction. So in the case of a friction, you'll always calculate the work to be negative. And what I mean by that, if we look at here at Pippin releases the seeing stone, it rolls down the corridor. The force of friction is 4 newtons, and it comes to a stop over a distance of 14 meters. Determine the work done by the floor on the stone, because it did do work, but it did negative work because it slowed it down, right? So when you do the calculation, you sub in the numbers, the 180, if just a quick thing, there's no angle given in the question. You don't even have to bother with this, okay? But cos of 180 is 1, so it's all good. It's -1, actually. That's why it works. But you get a negative number. But if in doubt, if it's friction, make the work negative. That's all you do. Okay, so energy, out of work and into energy, I said this before, it's the ability to do work, right? It's the ability to make something move, accelerate. But we do break it up into 2 types. One is kinetic energy, which is actually doing work, moving. So you have kinetic energy if you're moving. And the other is stored energy. And that's like your sandwich, right? Your lunch, giving you energy to exercise. It's gasoline in your car. There's lots of different types as well. In elastic band, if you stretch the elastic band, at that second it's got potential energy. It's got the potential to move. All you gotta do is let go of the band and it'll fly across the room, right? That's potential energy. And then it does work by moving. As far as kinetic energy is concerned, we actually have 2 types of kinetics. So you've got, overall there's 2 types of energy, kinetic and potential. Both of those are broken up into different types. So potential energy, there's tons of different kinds. We'll talk about that later. And kinetic energy is 2 different kinds. It's actually energy of motion, like you're actually moving, and by virtue of that, you've got kinetic energy. And the second type is thermal energy. And the reason is that thermal energy, something's hot because the particles in it are moving very fast. So those are the 2 types of kinetic energy. As far as potential energy, we're going to talk about, the only one in this group we're going to talk about very extensively is gravitational potential, because gravitational potential means you're holding a tennis ball up above your head. As you hold it there, it's not moving. It doesn't have kinetic energy, but all you got to do is let go of it. And if it falls, it'll be gaining kinetic energy. And so therefore, it's got the potential only because it's up high. So gravitational potential is the potential energy due to position. It's due to something being up high. And as far as roller coasters are concerned, for example, you think about the Leviathan or any roller coaster, it's at the top of that hill, and it's sort of the energy. They're called gravity-driven rides because they have gravitational potential energy. They're up high, and that's what gives them the energy to do the whole ride. Some chain pulls it to the top, and after that, it's just gravity that causes it to move. But other types of energy here, chemical potential, that's like the food in your stomach or your gasoline in your car. Magnetic potential, again, if you've held a paper clip somewhat near a magnet, you know there's an energy between them because you get it close enough, that paper clip will move to the magnet. So that means that just before it moves, it's got potential energy. Nuclear potential is the type of energy inside the atom, right? And it's like if you can split that, called nuclear fission, you can create a ton of energy, and that's what Bruce Power does. Solar energies is the energy in the sun, and you look up in the, you can feel that causing thermal energy on your face. If you look up at the sun, it gets warm, right? And then electric potential energy is what causes the lights to turn on. Okay, the most important thing we learn in the course, I think, is this right here, that the law of conservation of energy. Energy cannot be created or destroyed, only transformed from one type to another. So that means that, if you have a type of energy, and the example might be energy of motion in wind particles, air particles through wind, right? That kinetic energy of the wind particles causes a kinetic energy in a windmill, and that creates an electric energy. And we'll actually, in the next unit, we actually learn and understand how that happens. But the point is that, you're not creating electricity. You're just transferring it from the potential energy or the kinetic energy of the wind into electric potential energy. You always just going from one type to another. So let's look at the Leviathan, and we'll talk about the transformations that occur during the ride of the Leviathan, and that's why I have this open on my screen here. Oops, not the calories, this one. So just think about, while you watch, think about the energy transformations that happen. Somehow that's given, I think it's attached, doesn't look like it's attached to a chain yet, so I don't actually know what starts it. But you can see it gets hold, watch, and you'll see, it's interesting, I don't know what causes it to move now. But here you see the chain, right? The chain's coming up here to drag it up the hill. So at this point, there's a ton of electricity causing that to happen, right? So it starts with electric potential energy. This makes me sick watching it, by the way. But that energy, as you lift up, it's giving the Leviathan, it's giving the roller coaster itself. Yeah, I don't like watching this at all, actually. It's giving the Leviathan gravitational potential energy. Because as soon as that chain lets go, it's all just gravity that makes it work. So right at the top here, the chain lets go. Now it's got a ton of gravitational potential energy, and that's all going to turn into, holy cow, kinetic energy. Now it's moving really fast, right? It's got kinetic energy. And we can watch the rest of this, but the most important part is once you understand the first little bit, the rest is just sort of basic. And so it has kinetic energy because it's moving, and as it goes up high, some of that kinetic becomes gravitational. It causes it to slow down a bit, right? At the top of the hills, and it's a little bit faster at the bottom. That's because it's got gravitational at the top, as well as kinetic, and at the bottom, it's just got kinetic. It's faster. I won't go on this thing. I don't even like watching people go on it. Alright, so that's the ride. Set that down. Go back to our, almost done the note here, by the way, if you're thinking when's this ever going to end. But I do want you to answer these questions. Where does it have the most gravitational potential? The answer I'll tell you, I'm not going to write it down. The answer is at the top of the highest hill, right? As soon as it gets to that first hill, that's when it's got the most gravitational. That's when it's the highest. And that, by definition, is what gives you gravitational potentials, how high you are off the ground. It got that energy from the electricity in the chain motor, right? So electrical energy, it turned to kinetic as it pulled it up, but then at the top, it's really just gravitational. So this gravitational it has at the top of that hill, as it drops down, it becomes kinetic energy. And it has the most kinetic energy, because that's energy of speed. It has the most kinetic energy. So that just, what I'm really asking you there is, when is it going the fastest? It goes the fastest at the bottom of the first hill. And then the question of why is the second hill never as high as the first? And there's really two reasons. Even if you wanted the coaster to pretty much end, you would, if you had the second hill as high as the first, even if you didn't want it to have any speed at the top of that hill, it couldn't. And I hope you're thinking about the reason why, because the answer is why any process, it's impossible to have a perfect process, and the reason is friction. Some of the energy, I say that energy cannot be created or destroyed, but in a system, in your roller coaster system, because of friction, so your track warms up, the air around the track warms up, that's a little bit of thermal energy that's stolen from the roller coaster. And that means that at the beginning, the roller coaster will never have as much, or sorry, later on in the coaster, it'll never have as much energy as it started with. And then the other reason is that at the top of the second hill, it's usually got a lot of speed too, right? So at the bottom, it's just kinetic energy. At the top of the first hill, like at the very beginning, it's got just gravitational. It's got almost no speed, right? And then it speeds up. It's got tons of kinetic energy. And then at the top, at the next hill, though, it's got some kinetic because it's going fast, but it also has some gravitational, right? So it's the energy is split. Anyway, here's just something to have down on your sheet. Then what I was saying is the electric energy to begin, and you're always losing heat in the process the whole time, right? Everywhere there's friction, there's going to be some energy lost. But mind you, because this unit ends with you building a roller coaster, right? And then yours is going to be a gravity-driven roller coaster. And we do sometimes assume there's no friction because it makes the calculations easier. Anyway, so at the top of the first hill, it's got just gravitational potential. At the bottom of that hill, it's just got kinetic. And then sort of on the second hill there, it's got some kinetic and some gravitational. Anyways, that's a bit of a long note, but that is the introduction to energy, and I don't really have any assignments for you to work on yet. It's just, sort of absorb that, and then tomorrow you can watch the work video and hopefully work on your forces assignments.